discussion, the thing that needs to be determined is what is real. And what an evidence-based discussion is everything in this presentation is going to be based upon peer-reviewed research journals, laboratory studies, and field studies about Legionella. So as we begin, first a couple of reminders. Legionella is not new. The first incidences of Legionella occurred in building piping systems, occurred in the late 1970s. That's when they were discovered. And since that time, and pretty much very much through the early 80s and early 90s, there's been a ton of research as people were trying to understand what was going on with this bacteria, how it lived, and how it died. And as a result of that research, which has been validated over and over again, there were a number of risk reduction guidelines introduced. The first was in the United Kingdom way back in 1986. And the World Health Organization and the Department of Labor through OSHA have released their own guidelines. And of course, we're all familiar with the ASHRAE Guideline 12, which was published in the year 2000. The thing to keep in mind is, although there's a lot of recent talk about Legionella, the basic knowledge has not changed since that time. As I mentioned, this is really what's causing a lot of the talk about Legionella. After about 10 years of work, the ASHRAE task group published this in July of 2015. And what this is, it's a variation of hazard analysis critical control program, which has been used in food service for quite some time. It's primarily targeted to building owners, although there is a section for designers. For the building owner, it explains how you put a team together, how you document your plumbing system, identify all the things in that system that could be a potential Legionella risk, and what you need to do to mediate the risk. And not only do you have to write this down, but it also forces you to pay attention and to do what you say you're going to do. This is now a voluntary standard at this point, but it's going to be adopted into the next version of the International Plumbing Code. And once the International Plumbing Code becomes state law, it's folded into the building codes, state building codes, it in fact becomes a law. Now within this standard, there's nothing about how to design a system. And the designer's responsibilities, among all the other things you're currently doing, a designer merely needs to provide information to the owner on how to operate, install, and maintain the components in the building plumbing system to prevent Legionella. The actual design guideline that's referenced in ASHRAE 188 is this publication here, originally published in the year 2000, and currently under revision, expected to have a first public release July of 2017. And in this guideline are, of course, recommendations on the design, operation, and maintenance of a number of plumbing systems, including domestic hot water. And in addition to eradication procedures, should you find yourself with a building where you have Legionella contamination. So to get right to the point, to control Legionella in storage-type water heaters, it's actually pretty easy. You size the tank appropriately, and you keep the bottom of the tank clean of sediment, and both of these things help to maintain a residual chlorine level. And secondly, you size the heat transfer appropriately, and you maintain the recommended temperature of 140 degrees, and what this does is it maximizes your kill efficiency for the Legionella bacteria. So what would you think is the primary reason, the bottom line reason that a building water system becomes contaminated with Legionella? My computer just froze. Hang on just a second, please.
Oh, okay.
Yeah, there we go.
Good.
It wouldn't advance. Okay.
Okay.
Well, the answer to that question, well, because we were interrupted, let me go back. What do you think is the primary reason that a building water system becomes contaminated with Legionella? And the answer is old water. And what old water is, it's water that's been previously treated, but it's lost all of its residual chlorine, and as a result cannot protect against microbial contamination. Water that comes from treatment plants is not sterile. It's chlorinated to keep microbes under control and at certain levels, but there are microbes in the water. And once the residual chlorine level goes away, those microbes are basically can no longer be contained. This can occur anywhere in the building plumbing system, and it's caused by water that sits unused and unrefreshed. And a big contributor to it is branch piping, sections in the building piping where you branch off to certain zones with inadequate flow, perhaps. Chlorine decay itself occurs naturally, and it's unavoidable. And we're not able to predict in any given building exactly how long it's going to take for chlorine decay to occur, because it's contingent not only on the initial residual chlorine level, but a number of factors that are unique to each water system. Specifically, the condition or age of the building water system, which means how much corrosion is there in the system already, how much contamination do you have in the system already. Another contributor to chlorine decay is surface area to water volume ratios. Unlike the transfer of water from the building treatment system to the building, where the pipes are very, very large, buildings are unique in the fact that they are the building piping system is much smaller diameter pipe, and when that occurs, you have a much greater surface area to water volume ratio. That increases the depletion of chlorine, because chlorine essentially has a greater opportunity to contact those surfaces, and chlorine actually reacts to both metallic ions and organic matter. So chlorine will decay in the presence of the piping materials that are used. Adding to this is forced and frequent contact, which essentially means pumping water through the system. The more contact with the surfaces, the greater the opportunity for chlorine to react. And another thing unavoidable with what we do for a living, which is water heating, is that as you increase water temperature, you also speed up chlorine decay. A loss of residual chlorine is made worse by a temperature drop, which can occur in the building piping. If the temperature drops to certain levels, particularly in the optimal growth zone for the bacteria, which is considered to be between 90 and 105 degrees, Legionella growth can be unopposed and be quite rapid. Now, how to combat old water? In the building piping system, what we do is we circulate water back to the heater, and this both reheats the water, and it also provides an opportunity to replenish the chlorine, which may have been depleted in the building piping system. And of course, where people are at very high risk of catching legionellosis are people who are severely immune compromised, such as acute care hospitals, and it's very common for supplemental chlorinators to be used. Now, here are some claims that are being made by the manufacturers of instantaneous water heaters, and we'll go into the details of these later. But first of all, no stored water. There's less of a chance of getting Legionella because they don't have standing water. Because they don't have standing water, oftentimes they suggest that they can operate at lower allowable set points. And they also say that by doing this, they're saving significant amount of money by improving the efficiency and reducing standby. And they also say that circulation, either through the building pump and or on the equipment itself, reduces or creates turbulence and keeps the exchanger clean of sediment and biofilms. So the question, is there a direct link between stored water and old water? The answer to that question is no. Old water, a loss of chlorine residual, is caused only by a lack of use and inadequate water turnover. The amount of water that you have in the system is irrelevant. You can have a 2,000-gallon storage tank in a particular building, and you will not have an old water situation because the water is being used, it's being refreshed. But at the same time, you could have a 2,000-gallon or even a 500-gallon, 200-gallon tank in another building where, because there's not adequate use, you can have an old water situation. Water heaters, among the other things to consider, is water heaters are the first thing that the water touches in the hot water distribution system coming off of the main in the street. And therefore, it sees the greatest amount of residual chlorine. A water storage tank, by design, provides a reservoir for free available chlorine, whereas instantaneous waters have little or no free available chlorine reservoir. And without a reservoir, circulating water through the building and back to the heaters won't solve an old water problem if the entire system is depleted of residual chlorine, because in effect, all you're doing is circulating old water. So, and sizing the water heater tanks is key to ensuring adequate turnover, so you avoid, and stored water, to make the point, doesn't mean stagnant water. And just a note about PVI in particular, how we size water heaters, is we calculate an hourly recovery demand, and then we apply a factor to that, either 25% or 33%, to determine what the tank is going to be. So we have a product that by design has a recovery capability that's 2 or 3 times greater than the storage tank capacity as far as hot water at temperature, which means that that heater is going to be turned over frequently during periods of high and even moderate use. Now, another thing, of course, said about the instantaneous heaters is because they don't contain water, they don't have to worry about things like temperature settings, and high temperature is something that only pertains to storage water heaters. Some notes about water temperature. At 140 degrees, Legionella bacteria dies much faster than 120 degrees. And the table right there shows you the time-temperature relationship to achieve certain kill rates. As a result of this, the difference is huge. And as a result of this, every single guideline out there recommends 140-degree water leaving the water heater. In fact, heater settings below 140 degrees are actually used in predictive modeling for Legionella contamination. And just a note, sanitized means the time required for a 6-log kill, or 1 million bacteria or colony-forming units per liter, which is an enormous amount of bacteria, something that you would never see in a building plumbing system, but what they can produce in a laboratory to determine these numbers. So in open water, Legionella is easy to kill. It's susceptible to relatively low levels of chlorination, which is common, 0.2 to 0.5 ppm. And it's also susceptible to elevated water temperature. But the problem occurs when the bacteria forms a biofilm, which is a community of a multiple number of organisms that essentially bind together in a plumbing water system for survival. In a low nutrient system like a domestic water system, bacteria will do this. And it's believed that 95% of the Legionella in the building plumbing system resides in biofilm. And biofilms are a problem because when they're thick enough, they can offer protection against both temperature and chlorine. Now, it's been shown in lab studies that 140-degree water, biofilms, can't support Legionella growth. The Legionella dies. But at 120 degrees, the Legionella survives indefinitely. And in addition to the Legionella, we need to be concerned about something else, and that is amoeba. Most of the multiplication of Legionella in a building water system is a result of the Legionella being ingested by an amoeba. The amoeba merely thinks it's getting lunch when it eats or ingests a Legionella bacteria, but the bacteria can reverse the enzyme action inside of the amoeba and actually begins to consume the amoeba from the inside out. The photograph at the bottom is an amoeba that's ate a single bacteria approximately maybe 18 hours ago. And you see the dark cells inside of the amoeba. That's Legionella bacteria that's basically been cloned and replicated. After a while, the Legionella bacteria consumes the amoeba and it breaks open, and all of those Legionella bacteria now infect the system. It's important to note that the amoeba have a temperature tolerance that is very similar to the Legionella. 30 minutes at 140 degrees provides a 100% kill, and as with Legionella, 120 degrees is far less effective. Now, more importantly than that, the residual chlorine that would quickly take care of Legionella in open water is not effective against the amoeba. You would have to use probably about 5 times the typical amount of chlorine you see in a domestic water system in order to eradicate the amoeba within about an hour. So temperature, because you don't have the chlorine level available to fight the amoeba, the temperature is critically important. And temperature and Legionella control, it's a time-temperature relationship. Now, in an instantaneous water heater, there's very little time because there's very little water volume. Water can move through an instantaneous water heater in, let's say, 30 seconds. That's not enough time you can expose a Legionella bacteria, for example, to 140 degrees for 30 seconds. But as we know from the table, that's not nearly enough time to take care of the problem. So to compensate for that short period of time, in an instantaneous water heater, the temperature should actually be increased. And anyone who's suggesting that an instantaneous water heater can be turned down is really thinking only about the water heater, and they're not thinking about the building plumbing system. Because if we look at this chart again, while it is possible at 120 degrees, after some hours to achieve, considerable kill rates, how confident are you that you're going to be able to maintain 120 degrees throughout your building plumbing system for that period of time? With storage water heaters, you have both time and temperature. Typically, the thermostat is located midway to lower in the storage tank, and any draw on that heater is going to cause that thermostat to call for heat. So you're able to maintain effective kill zone at all times in a properly sized water heater. Now, the claim that lowering the outlet water temperature on an instantaneous water heater to 120, saves significant amount of money is exaggerated. All of the commercial water heater efficiency tests, every efficiency number you see advertised for a commercial water heater is conducted with 140 degrees as the outlet temperature. And it's not the outlet temperature or a change in outlet temperature that affects the efficiency so much, it's changes in the inlet temperature. And also the standby heat loss as well is conducted with 140 degree stored water in the water heaters. And every water heater has to be ASHRAE compliant, and the amount of insulation required by ASHRAE today has greatly reduced standby heat losses. So does circulating water help reduce Legionella in an instantaneous heater, by reducing biofilm or keeping sediment in suspension? Circulating water, as mentioned earlier, is essential for the building piping because two things happen immediately when that water leaves the water heater and enters the building. It begins to lose temperature and it begins to lose residual chlorine, and you have to circulate it back to the water heater to reclaim both. However, there's no similar benefit for water heaters. This idea is perpetuating the myth that stagnation is the primary cause of Legionella in building plumbing systems. The fact is, there's no scientific basis at all to suggest that merely circulating water reduces or detaches biofilms, with the exception of flow rates and turbulence that are higher than you ordinarily see in building plumbing systems. You need to achieve flow rates approximately 10 feet per second to see an appreciable detachment of pre-existing biofilms. And 4 independent studies have actually confirmed that biofilm growth actually increases with increases in flow rate compared to no flow or low flow conditions. This seems to be counterintuitive, but the reason for this is because under a higher flow condition, the surfaces of the biofilm is exposed to a greater amount of nutrients and oxygen and other microorganisms that serve to increase the size, growth rate of the biofilm. Sediment and Precipitants. Back in 1986, laboratory study was done that showed there was a synergistic relationship between the sediment that formed in the bottom of a storage tank and Legionella. And it was primarily because the sediment is an ideal environment for the creation of biofilm. The bacteria, rather than forming on a hard surface, can actually infiltrate into something that's a little bit softer. There's a whole lot more surface area there, and this also provides a tremendous amount of protection from chlorine and temperature. So the removal of sediment from storage tanks has been shown to eliminate Legionella from subsequent water samples. So it's a very easy thing to do, and removing the sediment also frees up residual chlorine for use elsewhere in the system. You could imagine with sediment accumulation and biofilm in a tank, the entering residual chlorine is essentially used up trying to combat that. If you very simply remove the sediment from the bottom of the storage tank, you take care of that problem entirely. In instantaneous water heaters, the moderately turbulent flow rates, while not able to shear biofilm, are certainly able to suspend sediment and particles. And these particles can enter the building plumbing. And once they do, they're going to be very difficult to locate and remove. And the sediment that travels into the plumbing system has the same beneficial, beneficial living space for the biofilm. So you have the same problem, but in this particular case, you can't find it and remove it. Now, in a storage tank, as I mentioned, the low turbulence actually allows the sediment to settle at the bottom, where you can easily flush it out through a drain valve. So to review, instantaneous water heaters, excuse me, I'm getting some kind of a video coming across my screen. So to review some of the things that the industry claims being made about instantaneous water heaters, we don't have stored water, and that means less of a chance, of Legionella, because it's not stagnant water or water that's sitting around and getting old. In fact, with proper sizing, storage water heaters offer a high refresh rate, ensuring water turnover and return of residual chlorine, or maintenance of residual chlorine. Storage water heaters also provide a reservoir and the greatest amount of residual chlorine in the system. So storage water heaters also present less surface decay effect, because there's less surface area to water volume compared to instantaneous water heaters. The other claim, a lower operating set point is possible, and this of course saves money. Again, every guideline out there says that 140-degree water is what needs to leave the water heater and go into the building piping system. The brief time that water travels through an instantaneous water heater is not long enough to kill Legionella at low temperatures, because it is a time-temperature relationship. And this thinking considers only the water heater and not the entire building plumbing system. And finally, the claim that continuous circulation in a low water volume instantaneous heater creates the turbulence that can rid the heat exchanger of biofilm and sediment and reduce the growth of Legionella. This is really a myth. Moderate to high flow, as I explained, can actually increase biofilm growth relative to a no-flow condition. And while it is possible to have flow rates high enough to shear biofilms, these flow rates are simply not seen in domestic water systems. Flow rates through the heaters are, however, sufficient to carry the sediment and precipitant into the building, where, again, it's difficult to locate and can contribute to Legionella contamination. And when storage water heaters, the sediment is allowed to settle at the bottom, where it can be regularly flushed through the drain. So again, control measures for storage-type water heaters: size the tank appropriately, keep the bottom of the tank clean of sediment, and these two things help to maintain your residual chlorine level. Size the heat transfer appropriately and maintain the recommended 140-degree Fahrenheit temperature. This allows the greatest effectiveness of a kill. So if it's so easy to do this, why did storage tanks get such a bad reputation over the years? Well, from early site studies, it was very evident that storage tanks were oversized. There's site studies explaining that 2 or 3 storage tanks were in the mechanical system were essentially unused, but filled with water, and they rotated through them. So they were creating a situation where they had old water. Keep the bottom of the tank clean. Early studies constantly described water samples from tanks as water and sediment. Maintain 140 degrees. Many of the tanks were operated less than 140 degrees to save money or to avoid the use of mixing valves. Right? So why did this happen? Because back in the 1970s, when we first started discovering this, the operators of these systems just simply didn't know any better. They didn't know anything about Legionella, so they didn't know what to do to keep it at bay. And one last point, Aquaplex tank material. Studies show that Legionella growth is higher in water systems where there's an elevated iron level. And traditional storage tank construction is lined carbon steel, where over time the linings erode, and this results in iron release or contamination, corrosion, and iron release into the water. Aquaplex is a duplex stainless steel. It requires no lining, and it won't corrode in potable water. So that is all, if there are any questions.
Well, thanks, Paul. We do have a couple questions that came in. The first question, does a 1017 mixing valve defeat the purpose of keeping the water temperature at 140?
Well, what you're saying is, what's the difference between having 140 degree water leaving a water heater, particularly a storage water heater, versus because you're knocking it down to 120 degrees anyway, for example, is that the same as just having 120 degree water, just leave a water heater? Well, the answer is no, because you're losing the opportunity to kill any bacteria that's in the water heater that might try to migrate through. It has to pass through a temperature zone that kills it. So even though you're taking that 140 degree water and then blending it down to 120, you've given yourself every possible chance to kill the Legionella and the amoeba before it even reaches the mixing valve. Whereas if you just have water coming out of a storage tank at 120 degrees, there's a very good chance you have done nothing to eradicate those microorganisms.
Okay. And one more, I think you may have answered this one, but is tank lining a factor in Legionella growth?
It can be. Biofilms tend to form more easily on rougher surfaces. So there are, I don't want to really talk directly to that question, but one thing to consider is the surface roughness of the finished lining inside of the vessel. There are some methods of lining storage tanks that result in very rough surface finishes and more conducive to the buildup of biofilms.
Okay. All right. Well, thanks again, Paul, for the great presentation. And thank you, everyone, for joining us today. As I said before, later this afternoon, you'll see an email from myself and ASPE with your CEU certificate. If you don't see it, give me a call or shoot me an email. Some of you didn't put your full name in the login on WebEx. I think I know who you are, but if you don't see it today, just give me a call. I'll get it over to you. Also, look out for a recording of this class and all of our previous classes. You can find at our Disney-McLane and Associates YouTube channel. So thanks again, everybody, and hope you have a good week.